Hi, welcome everybody. This is going to be my second hot wash. We're going to talk about how glycogen metabolism is controlled and some of just the mechanisms that are used to regulate both up and down synthesis and breakdown of glycogen. So we're going to start off with just a quick review of glycogen metabolism. So it occurs by starting with anabolism. Start with glycogen synthase, which will add individual glucose molecules in the form of UDP glucose. And they'll kind of branch off of that to form the glycogen chain. The initial 4 to 7 glycogen or glucose molecules are linked together by glycogenin, at which point glycogen synthase takes over. And then additionally, branch points will be added by the branching enzyme. And those are the three, key enzymes for anabolism. For catabolism, the big enzyme is glycogen phosphorylase. So what we have there is that we are trying to take our glycogen and break it down into G1P, and that's the phosphorylation step. And then next we have isomerization, where we take our G1P and we convert it to G6P. And then from the G6P, we insert that down and into our glycolytic pathway. All right, now let's talk about the actual regulation step. Okay, so we have three main ways we can control our enzymes in the body. The first one is going to be phosphorylation, and this is the most powerful, the fastest, and kind of gives us the best control. This one, what we do is we add or remove phosphate groups. Usually there will be a serine residue, but it could also be theranine or other amino acids that can be phosphorylated. Our second mechanism is going to be through allosteric. This is where we're using other signaling molecules that are not phosphates to both enhance or inhibit the enzyme activity. And then the third kind of control mechanism we have is feedback inhibition, which is where our products build up, and this will prevent more reactions from occurring. This is kind of based partially on Le Chatelier's principle, as well as based on kind of the diffusional dynamics of the enzyme's active site. All right, so when it comes to phosphorylation control, the important thing to remember is that we have catabolism and anabolism that we can do, but they are opposing cycles, and so we really only want one at a time. But we can take advantage of the fact that they're opposing cycles and use similar enzymes to control them. So the most common ones we see are protein kinases. So we can phosphorylate both glycogen synthase and phosphorylase. It's important to note that the phosphorylated synthase is less active, while the phosphorylated phosphorylase, that's a mouthful, is more active. And then protein phosphatases are also used. They will remove the phosphate groups from the enzymes. So the dephosphorylated synthase is more active, and the dephosphorylated phosphorylase is less active. And when it comes to allosteric control, one big molecule that we have is epinephrine, which is shown to inhibit glycogen synthase. And the opposite effect of that is that we are going to promote the release of glucose from the muscular tissue. It kind of goes back to our fight or flight response. The other kind of mechanism that we have is we have glycogen phosphorylase will actually be enhanced by AMP and inhibited by ATP. So this makes sure that we're only breaking those glucose molecules off to break them down into energy when we need the energy. When it comes to feedback control, we can see that glycogen synthase is promoted by high amounts of G6P, and it's also inhibited by high amounts of glycogen, and that makes sense. If we have a lot of sugar we need to build and store, we'll want to store it. If we have a lot of glycogen already stored, we don't really want to store more. And then phosphorylase will follow a similar pathway. When we don't have a lot of glycogen stored up, we will have less enzyme activity. When we have less G6P, less free glucose in the body, we'll have less enzyme activity. And you can also kind of correlate this back to how much energy is available in terms of glucose, ATP, everything like that. When we have lots of energy, we want to increase our storage. We want to increase our glycogen synthesis, and we want to kind of stop breaking down glycogen into the different monomers like glucose. When we don't have a lot of energy, when we're, in a fasting state, we're going to increase our glycogen breakdown and glucose mobilization so that we can oxidize that fuel into things like ATP through oxidative phosphorylation. And so that kind of explains how feedback control can contribute to control over all of glycogen metabolism. All right. Thank you guys for your time. If you have any questions, feel free to reach out. Thanks for coming.